In this video, we're going to go a little bit further with solids of revolution. We're going to go into some cases that have a little ins and outs to them. And so let's just do a quick review of the simple cases that we've seen. The very first thing was the simple disks, and that was the simplest kind of region, the region under the graph of a function f of x from a to b, and we imagined a single rectangle being revolved around with the region to create a typical disk, and the volume of a disk is area of the base, which is a circle, pi r squared, times the height, which is delta x, or in the limit as n goes to infinity, where n is the number of disks that you have, dx. So right, that's area of the base times height. And the formula that we came up with for this, the official sort of formula for this situation is right here, the integral from a to b of pi f of x squared dx, but it's typically more helpful to think of it in terms of this formula here, pi r squared dx, where the radius is the function value. The next thing we looked at was simple washers, and the washer case differs from the disk case in that there is also a lower bound, so that the region is bounded between two functions, f of x and g of x, from a to b. And we did the same thing. We took a single rectangle and we imagined that revolving around the x-axis with the rest of the region to create a typical washer this time. And the thing about a washer is that there's a hole in the middle, and so you have to subtract out that hole. And so you've got, instead of pi r squared, pi r squared, big R squared, the outer radius, minus the inner radius, the small radius, dx, or in terms of the functions that we have here, the volume is given by the integral from a to b of pi times f of x squared minus g of x squared, right, pi times the whole thing. And here, to relate these things, are the outer radius, the bigger radius here is our function f of x, and little r, the inner or smaller radius, is g of x. So those were the two simple cases, disks, and washers. Now we're going to play around with some things that can change a little bit the formula, but this big formula here, the formula of washers, is kind of the most general. And if you don't specify the functions involved, if you think of it only as the outer radius and the inner radius, and you sort of figure out how those things are geometrically situated in each of the regions or each of the situations to follow, it all kind of comes out. So the first kind of new case that we're going to look at is, what if the axis of revolution, what if the line that we're spinning our region about isn't the x-axis? Right, the x-axis is y equals 0. What if we take y equals some general k value? So we take a look at this picture here. Here's our same kind of region, right, with an upper bound and a lower bound given by functions f of x and g of x respectively. We're now going to rotate that region around a general line y equals k and take a look at what happens. So we're still going to get a washer. It's still going to be hollow in the middle, right? So this is still hollow through the center right there. But now the radius, the big radius and the small radius are no longer just the function values. If you do the length, right, you want to see the length of this radius, so you're taking its high value minus its low value, or the top minus the bottom. Well, the top is still the function value, right? The top is still the function value right up here. Right, that is still our function f of x as our outer radius, but the bottom function is no longer y is equal to 0, it's y is equal to k. And so the top minus bottom gives us f of x minus k. And notice that if we had the x-axis, right? The x-axis is the line y is equal to 0. And if that's our k value, then we end up with, right, we end up with exactly just the same f of x that we had before. Same thing with the lower bound. That lower bound here is the top value of the radius minus the bottom value to get that full length of the radius, right? We are talking here about wanting radius values that are positive or, well, non-negative. So we want r to be greater than 0. So we're always doing top minus bottom or high minus low values for this. So for the inner radius, the small radius, the top value is our function g of x, whereas the bottom value is still the axis of revolution, y is equal to k. And if we put that information back into this same general formula, pi times big R squared minus little r squared, well, if we fill in those two radius values, right, these guys right here, into the values, then that's what we get. So the integral from a to b of pi times the bracket f of x minus k all squared minus g of x minus k all squared, and compare that to the original value when k was 0, and we, it comes back to the same formula. So this is like an extension of that formula. So that's the first new thing. What if we're revolving around a different axis of revolution? Let's look at yet another possibility. Oh, wait, before we do, I played a trick on myself. What if k is above the region? If k is above the region instead of below the region? Well, it's the same principle. It's the same principle, except now the top value and the bottom value, right, they switch. They switch compared to the last one. The top value of the radius is the axis of revolution, y equals k. And the bottom value is the function value. So for the small radius, the inner radius, we have k minus f of x. And for the outer radius, the radius in green here, top value minus bottom value. Top minus bottom gives us k minus g of x. Plug that back into the same formula that you did before, and you get this integral, which is very, very similar, just with slight tweaks about which function is on top, which is on bottom, because you always want your volumes to come out to be positive volumes. So now what if a new situation again? What if the region is bounded by more than two curves, right? So what if we don't just have f of x and g of x, but we also have h of x, and maybe more of them even, right? But we've got some amount of curves that is greater than 2. Well, we looked at this when we did area. And let's just remember what we did when we did area. We looked and we imagined that we were drawing our rectangles for Riemann sums. And those rectangles, we had to look at the top value. We had to look at the top value minus the bottom value. And in different parts of the region, the top value landed on different curves. And for every pairing, right, for every pairing that we had, right, so for this region, all the rectangles here in region 1, as I've drawn it here, are going to be between the blue curve on the bottom and the red curve on top. So all the rectangles in region 1 will be calculated by using top minus bottom, f of x minus g of x. Similarly, in region 2, the same thing happens, but where top values are now h of x. The h of x values are on top, and the g of x is still on bottom. So in area, we had to split this up. We had to split this up into two integrals and add them together. So since our volume is based on the rectangles in area, the exact same thing is going to be true. The exact same thing is going to be true. We need to set or split our solid up into two portions based on where the rectangles lay and where therefore the washers are going to lie. And so the exact same pairings here, where we have rectangles, this time it's not the height but the radius values here. So for the rectangles, for the washers in section 1 of the solid, the inner radius, the small radius, goes until the blue curve, and the large radius goes until the red curve. And so we are going to again use or base ourselves on volume is the integral from a to b of pi big radius squared minus little radius squared dx. But we have to do that twice because the top and the bottom values change, and add our values together. So if we look in region 1, the big radius, the radius in green, is the top value f of x minus the bottom value, which is the axis of revolution, k. The inner radius, which is the radius in purple, is g of x minus k, and then I use the exact same formula here, but I'm very careful to integrate this over only the part of the solid where those curves are the boundary curves of the region. And then I do the exact same thing in the next part. The big radius now goes to the brown curve, h of x. So h of x minus top minus bottom, h of x minus k, and the inner radius still stays at g. Right? So rather than memorizing formulas, it is probably better to understand this geometry and figure out how things are lying, what the big radius is, what the small radius is, and do top minus bottom in each case to figure out those radii. One more wrinkle, because why not? It's always fun to do a little bit further. All of this, absolutely all of this, can be done also using horizontal slicing. There's nothing that we have talked about in volumes that could not be done integrating with respect to y. So we remember that horizontal slicing means our rectangles are horizontal, which means that the delta x becomes a delta y, and then as we go into the limit towards infinity, a dy. So we are integrating with respect to y. So what do we have here? We're going to do an example that sort of puts all of this together, but is going to be using horizontal slicing. So let's read this example. So we're asked to set up the integrals that represent the volume of the solid when this region, the region bounded by y equals x, so there's that curve there, y is equal to minus x plus 6, y is 1/3 x plus 2/3, that's that curve there, is revolved around the line x is equal to -1. The region is given below, right? But that is a gift. That's a little bit of a gift. It need not be given. You may very well need to graph that region yourself, and you may very well need to figure out what these points of intersection are so that you can know the bounds of your integrals. Okay, so here's our solution. We are going to be revolving around the line x is equal to -1. X is equal to -1. We are told that we need to integrate with respect to y. We need to cut these solid into slices that goes through the axis of revolution, and so we're going to be integrating with respect to y, which means that all of our functions need to be expressed in the x equals g of y format. Okay, so we've got the first one there that I've solved. If y is equal to x, well, x is equal to y. If y is minus x plus 6, then x is 6 minus y, and if y is 1/3 x plus 2/3, x is 3y minus 2. So I do this and I see that depending on where our rectangles are drawn in the solid, that there are different boundary curves. And we see that in the first part of the region, right, up until here. So from here up until here, curves on the right, or the boundary curve on the right is 3y minus 2. The boundary curve on the left is x is equal to y. In the second part of the region, so going from the same line here now to the top, any rectangles in that region, when they're spun around, will have different boundary curves. They will have the brown curve on the right, and again the red curve on the left. So we're remembering that when we're doing horizontal slicing, if we want positive values, we do the right curve minus the left curve, because we're doing the greater value, right? This is the bigger value. The bigger value is on the right minus the smaller value. So we're always doing right minus left. Now our axis of revolution is x is equal to minus 1. So we are doing exactly the formula. So the integral from a to b of pi times the big radius minus the small radius, big radius squared, small radius squared, dy this time. So let's take a look at these values. This is here. This is the big radius squared in the first part of the solid. The radius goes from the axis of revolution to the outside of the solid. So 3y minus 2 minus 1, the axis of revolution. Over here is little r squared. And so here the inner radius, the smaller radius, goes to the curve. Right? The smaller radius, white is not a good color. Let's go blue. The smaller radius goes from the axis of revolution to the inner curve. So we have y is our inner curve, and minus 1. So the right minus the left. The same thing in the next integral, right? This is the big R squared. This is the little r squared. And now the boundary curves have changed on the right. Now we have this curve here, 6 minus y. So right minus left, 6 minus y minus 1. And then on the inner curve, we still have y as the inner boundary, so y minus 1. And luckily, we're not asked to evaluate, just to set up. And in fact, we're not even going to simplify. We're just going to leave it right there, because our train of thought is nice and obvious that we've done right minus left, and it's actually much easier to see what has gone into creating this integral than if you multiplied everything out and obfuscated your work.